The last topic that we're going to cover in this chapter is tidal energy. Um, I normally also cover some aspects of wave energy, but I am going to limit the end of this chapter to just tidal energy. So, tidal energy. Tidal energy uses the rise and fall of the tides to indirectly generate electricity. So, in principle, the harvesting of energy from the tides is similar to hydropower. A high tide, at high tide, a reservoir is charged, and at low tide, the reservoir is discharged. So in both the charging and discharging processes, a turbine can be used to generate electricity as much as other hydroelectric facilities do. The simplest tidal system is called the EBB generating system, and it uses a dam, usually called a barrage, across an estuary. So these gates open and close to regulate the flow into and out of the reservoir. So the tides are described based on their schedule and range. So their range is the elevation difference between the high and low tide, and the schedule includes the times of occurrence of the high and low tides. So a lunar month is 29.5 days. So a lunar day is 24 hours and 50 minutes. During a lunar day, the tides rise and fall twice. A tidal cycle is thus 12 hours and 25 minutes. This means that high and low tides do not occur at the same time every day, but progress 25 minutes per cycle or 50 minutes per lunar day. Also, the range is not constant but varies during the lunar month. So the maximum range occurring at the time of the new and full moons, and the minimum range occurring at the first and third quarter moons. So at a given location, the average ranges are complicated but predictable. The maximum range is called the spring tide, and the minimum range is called the neap tide. Here is a figure that looks at the typical monthly tidal ranges. You can see here the neap tide and the spring tide over the course of a 29.5-day lunar month. So, like anything for any renewables, you need to have a control strategy. And the control strategies in tidal energy is used to maximize tidal energy. So the consideration of how to distribute the generating time based on the tidal range for a given day impacts the size or the outputs of the turbine and the system total output. So here, for example, is a tidal pool schematic. You have here high tide level. Here, this is the area of the pool, of course. This is the turbine and the gates, right? Turbine and the gates. And you have here the tidal range, which is between the low tide level and the high tide level. You get what's called the tidal range. So the difference in elevation due to the tidal range determines the energy stored in the pool, where is basically going to be a function of the tide, the tidal range, sorry. So if all the tidal pool content were discharged rapidly, then the energy attainable would be the maximum, right? So if I were to go take this pool and the tide between the high tide and low tide, and all this water were to exit all at once, that would give me a maximum possible energy. However, if the pool were gradually discharged, then the low tide datum would increase and the high tide elevation would decrease, and available energy would be also decrease. So basically what I'm getting at is that there are two protocols associated with tidal discharge strategies. One is a simple tidal pool, in which the discharge is rapid and the conditions of this equation are fulfilled. The second is a modified simple tidal pool, modulated simple tidal pool, in which the flow is varied over time and the energy is recovered is less than the maximum, but you get more sustained energy. So again, although protocol 2 results in less energy available than protocol 1, protocol 2 has major advantages. First off, protocol 2 requires smaller turbines and results in more uniform power level applied to the grid or for local use. And protocol 1 results in large spikes of electrical power that occur at high and low tide. So basically, this protocol 2 allows for a more consistent power extraction, even though it is at a lower numerical value. So here you have the equation that is used to quantify the amount of energy you can get from the from a modulated protocol approach. Basically, it's looking at over time in the tidal range, the amount of energy that you can get. And there's some factors in here, such as this here it is, the parameter A. A was something that is used to control the slope of the tidal pool filling, and R is the tidal range. So all this equation is developed from according to this modulated protocol for power extraction. So quick problem, just to look at this as an example. We have here example 14.3 from your book, and it states, investigate the energy available from protocol 1 and protocol 2 per square kilometer of surface area if the tidal range is 12 meters and A is quantified as 0.0625 per hour, and the energy is harvested between a time of 1 hour and 4 hours. And how does A influence the energy harvested? So I'm not going to go ahead and fill in all the math, but if you were just to go ahead, just use this as a quick, you're going to look at this as a quick comparison. For protocol 1, right, you get the energy is going to equal 1/2 g gravity rho times the area of the pool times r squared. Basically, from that protocol, what you would get is a total of 201,000 kilowatt hours, right? And that's per square kilometer if you fill in 1 square kilometer for A. Again, that's for protocol 1. If we were to look at it for protocol 2, right? Protocol 2, assuming that A is equal to 0.0625 per hour. Again, this is work for protocol 1. Protocol 2, I'm not going to fill in the whole equation, but this would be for if you were to go ahead and spread the power extraction from a time of 1 hour to 4 hours, you would get a total of 20,000 kilowatt hours per square kilometer. So again, this value, of course, is 1/10 of the value from protocol 1, but the idea is that you're able to extract that power over a longer period of time. Right here, you have a graph that kind of shows you what the the total power you can get in kilowatt hours for protocol 2 as a function of that control parameter. And you can see that there's an optimum value that can be used in order to extract the maximum possible power over a period of time. This table from your book kind of gives you the tidal range for various areas in the world. You have here, for example, in Canada, the Bay of Fundy The vertical tidal range of 16.2 meters, which of course would be around close to 35 feet. And then under that, you'd have the United Kingdom, you have a few in France, Argentina, then Russia. Again, these are just different areas where tidal power, where they have high tidal ranges. This table is interesting. It gives you the data for existing tidal energy facilities. So you have one of the largest in the world, which is in France, can develop upwards of around 240 megawatts with a basin of 22 square kilometers, where the mean tidal range is about 8.5 meters. And then it shows you one also for Canada can generate 18 megawatts. But you can see the difference between the most from the one that produces the most power versus the second most power. It's a huge difference. And then you have one in China and Russia as well. So you can kind of see here, just 8.5 meter tidal range can produce about 240 total megawatts. That specific power plant, that specific tidal power plant in France is actually located near Saint Michel, which is in Brittany, not far from Nantes. It became operational in 1967, and it's operated without really many major breakdowns. And annually, it produces over 600 million kilowatt hours of energy. The facility itself has 24 turbines, each of them producing 10 megawatts. And the dam, the barrage, is 750 meters long, so it's nearly a half mile, 13 meters high, and as indicated in the table from the prior slide, the pool itself has an area of 22 square kilometers. This power plant is operated for more than 160,000 hours and has produced electricity that has been very economically competitive. The main company in France, called Électricité de France, has recently been carrying out a general overhaul of the equipment, including the installation of 3 new turbines per year until all the originals have been replaced. And this ends the lecture for video for part 3 of chapter 14 on ocean energy.